Last time we showed that sigma 0 and sigma 1, i.e. Turing machines, are closed under union. What we'd like to do today is show that they're closed under concatenation. And actually, let me take a little diversion there. Do I want to do that? No, okay, yeah, we'll do this. Okay, we'll do this first. Okay, so we've already shown that sigma 0 and sigma 1 are both closed under union and intersection. Now what we want to do is show that they're closed under concatenation. Okay, and recall what concatenation means. It means that AB is inside of A circ B if and only if A is inside of big A and B is inside of big B. So for instance, if we had one machine that was checking to see if something was something that Batman says, and another one looking to see if it's something that Mr. Darcy says, then a phrase that would be in both of them would be something that was something that Batman says followed by what Mr. Darcy says. So that would be something like, I'm the Batman, and does Darcy have any famous quotes? I don't really know. Okay, well, maybe I don't have a good analogy for that. Okay, so recall the way that we did this for context-free grammars. It was trivial, because what we could do is we could just say that C.S was just A.S followed by B.S. Concatenation is essentially built into context-free grammars. Now with NFAs, what we could do was we could make a machine that has an epsilon transition to A, which has an epsilon transition to B, which then has an epsilon transition to the accept state. And that was really straightforward to do. And then we got the DFA version of this by compiling the NFA. Okay? But we want to do the same idea with Turing machines. Now, unfortunately with Turing machines, it's not obvious exactly what we should do, because the thing about a Turing machine is that we want to run one machine, and then when we want to run it on just like part of the input, and then when it's done, we want to run the thing after that, but how do we know how to split up the input, right? Because it doesn't really make sense exactly how you might do that, because remember, the idea is that our input string has to be divided up into two pieces, the A piece and the B piece. And one is going to be sent to the A machine, and one is going to be sent to the B machine. And where exactly is that division, we don't know beforehand. So what we're going to do is we're going to do this by creating non-deterministic Turing machines. Non-deterministic Turing machines. And non-deterministic Turing machines are going to use a strategy similar to this one. But actually, I just remembered that I did want to mention something similar, which is that circ is also used, in regular math to talk about function composition. And we can actually kind of easily show that function composition works in Turing machines. Because basically what we want to do, remember, to compose a function, we would say that f composed with g, okay? So f composed with g of x equals y if and only if, when we call f on calling g on x, we get back y. Okay, but what does it mean? That means that there's some other value, z. That means that, if and only if g of x equals z, and f of z equals y. Okay, but now converting this to Turing machines, that means that if we have epsilon, and we start at g q0, and we get x as input, then we run for a while, okay, and then we get some string w, and we get g's qa, and then we get z there. Then if we take epsilon and we run on f's q0, looking at z, we run for a while, and then we'll get some other string, w prime, and we'll get f's qa and y. Okay? So it's fairly straightforward what we need to do. Basically, the way that we can do function composition is we can run g, and then when it's done, all we need to do is add a little extra step that goes and erases w and turns it into epsilon. It just says, okay, you're at the accept state. Here's what you need to do. You need to remember where you are. Maybe you could move left and change that to one special character and then go erase everything there, just turn everything into blanks. And then come back And then once you come back, then you will then run f's machine, and then you're good to go. Okay, so that would be an example of what you could do. All right, but what we want to do is we want to talk about not function composition, but concatenation. And to do that, we're going to get non-deterministic Turing machines. Now, I feel like what I want to do this time is to show you why non-deterministic Turing machines is going to let us get composition, and then we're going to go back and actually establish really what a non-deterministic Turing machine is. Okay, so the key idea is that let's suppose that we have a function. We're going to say given a Turing machine M, where the language of M such that the language of M is equal to A, and given N such that the language of N is equal to B, then what we're going to do is we're going to say that concat of Mn is going to be the following Turing machine. Here's what we're going to do. We're going to say given input x, okay, so we're going to get some input x. What we're going to do is we're going to split it into x equals uv. And we're going to do that in all possible ways non-deterministically. And I'll talk in a moment about how exactly we do that. Then what we're going to do is we're going to run m on u, and we're going to run n on v, and then we're going to return except if both accept. And we're going to return reject otherwise. Return reject otherwise. All right. Now, how exactly do we do this? Well, we're going to have tape 0 be the input, x. Then how do we split them non-deterministically? Here's what we do. We basically non-deterministically decide between two choices. Choice 1 is take the division we've done so far. And when I say take the division we've done so far, what we're going to do is we're going to have the head at some position in the input. And what we'll do is we'll say that everything ahead of us is going to be v. And everything that we haven't looked at is going to be u. And the way that we're going to do that is we're going to have another tape, tape 1, and so we're going to non-deterministically decide between the two things. Thing number 1, we will take the current character, turn it into a blank on tape 0, and then copy it to tape 1 and leave it alone. Or option 2, we're going to say that we're done and the division that we've done so far is good. And if we choose that, then what we're going to do is we're going to go to tape 1, and we're going to rewind the tape back to the beginning so that we're looking at both of them. So now we're looking at u on tape. So basically the idea is that it starts off with input is x and tape 1 is epsilon, and then we're going to change it so that tape 0 is v and tape 1 is u. Now we've non-deterministically decided because we keep deciding between those two options. We keep flipping a coin, and whether we keep going, that determines where the division was. And then if we ever get to the end and we've tried all of the divisions, then there's no more, and then we stop, and there's only one option, which is die. Okay, so then how do we run these different machines? When I say run the machine, what I mean is we just take the delta rules for M and we just like copy them over the way that we copy them over for the multi-tape Turing machines. And same for the N one. It's just that that Turing machine is only talking about one tape, and we just make it so that this one's talking about tape 1 and this one's talking about tape 0. And then if this one gets to the accept state, then we evaluate this one. And if it doesn't get to the accept state, well, then we ignore it. Okay. And because we did this non-deterministically, if M goes off into a loop, then, we'll never look at N of it, but because we did it non-deterministically, we'll just try a different division, and we'll try all of those different divisions simultaneously. And if we ever get through all of them, then we'll reject, and then we'll be done. So what this does is we now know that if we had non-deterministic Turing machines, we would be able to get concatenation, which is great. So now how can we actually represent non-determinism in the Turing machine? So recall that a normal Turing machine's delta function is q cross gamma arrow q cross gamma cross LR. Okay? Now, the simplest way to represent non-determinism is to represent it like this, where we say q cross gamma arrow power set of q cross gamma cross LR. That's the simplest way to do non-determinism, because you can just do all of these for different options. However, I prefer to have a simpler version of non-determinism that we're going to call 2-determinism. And 2-determinism takes a q cross gamma, and it returns either of two different things. It can either return a q cross q, which we're going to call a fork, or, and that's what plus means, or it's going to return a q cross gamma cross LR. Now, what's the idea behind this? How does a fork work? The idea behind a fork is that it's just like the system call in Unix, where you call fork, and on one side you're the copy, and on one side you're not the copy. And so the idea is that any situation where you, in this real non-determinism one, so like imagine we had non-deterministic, and we called, let's write delta ND for non-deterministic. Then we call QI and C. Well, what's going to come back is it's going to come back some set of things. So maybe it comes back with QJ, and then we're going to write A, and we're going to move left. And then we also get QK, and we're going to write B and move right. And then we also get QH, where we're going to write D and move left. Okay, so there's a whole bunch of options. Well, the way that we convert this to 2 non-determinism is that you can kind of think of this as this picture, where we have QIC goes to one option, which is QJAL. It goes to another option, QKBR, and it goes to a third option, QHDL. Right? Well, what we're going to do is we're just going to rearrange this. So when we see QI and a C, then in that case, we're going to split this up into 2 possibilities. One possibility will be Q1C, and the other one will be Q2C, right? Let me slide up a little bit. Actually, let me just rearrange things. Oh man, moving things around is awesome. We'll move that, and then we'll move this one, and then we'll move this one. All right, and then let's move all this stuff. Okay. So then in Q1, what that one's going to do is let's just have it so that that actually does the QJAL action. And this one forks again, and it goes to Q3C and Q4C. And then this one does QKBR, and this one does QHDL. So anytime we had a non-deterministic thing over here, we can easily do a corresponding thing over here. And then the only other situation that's weird is that when delta ND equals empty set, and then if it equals an empty set, then all we do is we just return a fork where they both go to reject. And so that way we can just kill both of them right away. Okay, so 2 non-determinism is a simpler way to think about the different things that's going on. We basically have either one choice or 2 choices, so it's simpler that way. All right, so then now we can write down the rules for explaining what a non-deterministic machine does. So what we're going to do is we're going to describe these rules in 2 different ways. Yeah. Should we describe it in 2 different ways or 3 different ways? Um, yeah. Let's describe it in 2 different ways. So one thing that we could do is we could have a non-deterministic semantics. Non-deterministic semantics. So what a non-deterministic semantics means is that the non-determinism that is present inside of the machine is reflected by non-determinism in the model. So what does that mean? It means that we have rules like the normal rules, that say that delta QIA equals QJBR. If that happens, then we can go from X QIAY, we can go to X B QJY, and then we'd have another rule for going left and another rule for adding blanks, just like normal things. But then we're going to add 2 more rules. And what these 2 more rules do is they say, well, what if delta of QIA, what if it returns a fork of a QJ and a QK? Well, in that case, we could do X QIAY would go to X QJ AY. That's when we do the left fork. And then there's another rule, a totally different rule, that says if delta QIA equals QJ QK, then we can go QIAY, we can go to X QK AY. And this is the right fork rule. Now, what this non-deterministic semantics does is it allows us to look at a Turing machine and describe what it is allowed to do. And we describe what it is allowed to do by saying, well, it can either go left or it can go right, but we're not actually saying an algorithm for determining which thing it actually does. And so a non-deterministic semantics like this is a great way to explain the meaning of it's a great way to explain the meaning of a non-deterministic program. However, it's not a good way to actually run it, i.e. it's not a good way to convert it into a Turing machine. So how then can we convert it into a Turing machine? Instead, what we want to do is we want to give a deterministic semantics for non-determinism. Now, how can we do that? The basic problem that we have to do, well, first of all, we kind of did this before, remember? We did this when we talked about the semantics for NFAs. This right here is really the oracle model for NFAs. And with NFAs, we also had the forking model. And the thing with the forking model, though, is we knew that the frontier of the forking model was finite because it could only ever be the subsets of the power set, elements of the power set of Q. And so that allowed us to produce that compiler. However, with Turing machines, though, it's not just the states themselves which are on the non-deterministic frontier. It's actually the entire configuration. The tape before and the tape after. Everything is part of it. And that set is not finite, it's infinite. So that means that we can't play some game and trick everything down. The key thing that we need to do then is we need to think about how to basically explore this potentially infinite non-deterministic space with some finite strategy. So what I mean by that is that we have some start configuration. This start configuration is epsilon Q0W, right? And then what happens is that maybe it starts off with a fork. And then maybe after the fork there's a straight thing, and then maybe over here there's a fork, and then here there's a fork, and then there's straight, and then maybe that's a fork. And the thing is that there could get answers, like maybe this is a no. But maybe there could also be loops where maybe this goes back to this exact spot. Or maybe there is some sort of infinite path which is diverging. Okay? Or maybe there's something that is infinitely wide. When I say infinitely wide, what I mean by that is that maybe it forks and then forks and then forks and then forks, and it does that forever. But maybe one of these paths eventually gets down to a yes. What we need to do is we need to explore this entire space and find that yes if it's there. Or what we need to do is we need to check and make sure that every path leads to an X. So we say yes if there's a yes, and we say no if every path is a no. Now, an analogy that I like to use for this is to think about how you explore a maze. So imagine that I write a maze. I have no idea how to draw a maze. I'm going to draw a really bad maze. So imagine that this is our start and this is our end. Okay? And I'm going to make like a really stupid maze. So what I'll do is I'll put a bunch of points in here. And then what I'll do is I'll add lines in. Whoops. I just made it so you can't complete the maze. Okay, so there's our maze. Okay, so how can we discover the exit of this maze? How can we go from here to there? Now, obviously, this is a really stupid maze. You know what I mean? But if you're like plopped inside of like a hedge maze or something like that, how do you find your way out? Well, there's this really common strategy that people do, which is that they follow the wall. So they'll do something like this. They'll go like this. They'll go, all right, I'm going to follow this wall. And by following this wall, I know that I will eventually leave. And they can follow the right-hand wall like I did, or they can follow the left-hand wall. And no matter which wall they choose, they will eventually exit. Okay? So, following a wall is a depth-first search through this graph. The problem with a depth-first search of this graph, however, is that imagine that we do a depth-first search and we happen to go down here, we see that X, and then we come back, and then, oh, we're going to go down here, and then we just keep exploring the same space over and over and over again. Or maybe we follow the depth-first search and we go down this infinite hallway. This would be like if we were exploring like a fractal, where you could be following a wall, but the wall is infinitely long and you'll never get to the other side of it, or the other edge of it. So a depth-first search can't work in something like this. Instead, what we need to do is we need to do a breadth-first search. The way that we can do a breadth-first search is essentially to look at each level of the tree separately. So we look at all the nodes that are 0 from the beginning, then all the ones that are 1 from the beginning, then 2 from the beginning, then 3 from the beginning, and 4 from the beginning. The analogy inside of a maze, is to say something like, okay, well, what I'm going to do is I'm going to explore all ways of walking 0 steps, then all ways of walking 1 step, then all ways of walking 2 steps, then all ways of walking 3 steps. And we can describe these different ways of walking steps as binary numbers. Now, what is a binary number? So for instance, imagine I gave you the binary number 0, 1, 1, 1, 0, 0, 1, 1. What would this mean? This would mean you're going to take 1, 2, 3, 4, 5, 6, 7, 8 steps. Okay, so you're going to take 8 steps. And then when you take 8 steps, if the first thing that you come to is a fork, take the left path. But if it's not a fork, then just keep going. And if you come to it, then if the second thing you come to is a fork, take the right path. Basically, 0 means take the left path, 1 means take the right path, and if it wasn't a fork to begin with, just keep going. So clearly, every node inside of any binary tree like this is described by one of these numbers. And so if we look at all the numbers of length 0, and then all the numbers of length 1, all the numbers of length 2, all the numbers of length 3, and so on, we would eventually explore everything inside of here and we'd get to the end. So that would be one way of guaranteeing that we would eventually get to the end. Doing that, however, requires that once you get to the end of this set of instructions, you go all the way back to the beginning and you try again. A way to think about that is that you're essentially trading time for controlling the amount of space that you use. Basically what you're doing there is you're saying, I'm going to repeatedly re-explore this upper part of the maze over and over and over and over again. And by repeatedly exploring that, I at least know that I'm going to have a finite set of the maze to begin with. So we can model this in the following way. We can say that configurations are going to be the path that we're on right now, and then the rest of the path, and then we'll say the input, the path that we're on, the rest of the path, and then the current tape. The current tape, really the current configuration, the current config. So the idea here is that we would start off, and if we're gonna see if W is inside of the language of some non-deterministic Turing machine, then what we're gonna do is we're gonna start off with C0 or configuration being W, the path is epsilon, the rest of the path is epsilon, and then the current tape is epsilon Q0 W. Okay, so that's configuration 0. Then what we're going to do is we're going to say, there's sort of a rule that says whenever the rest of the path is epsilon, add 1 to the path. So we'll say something like W path P epsilon configuration doesn't matter what it is. It's going to transition to the inputs W. The path is now P plus 1, and P plus 1 is the rest of the path, and then the configuration starts off as epsilon Q0 W. All right. Then what we do is we say that if the input is W, the path is P, and then we have a 0, and then the rest of the path, and then we have epsilon, sorry, and then we have X, Q, I, Y. Then what we're going to do there is we're going to go to W, P, R, and then we're going to go to X prime, Q, J, Y prime, where X, Q, I, Y goes to X prime, Q, J, Y prime using left, right, blank, or the left fork rule. So we can only use those 4 rules. We can go left, we can go right, we can do blank, or we can use the left fork rule. And then there's another one that says that if we get to 1R, X, Q, I, W, okay, then we go to the exact same thing here, but now we can use left, right, blank, or the right fork rule, right? And then we have one more rule that says that if we ever get to, if we have W, P, R, X, Q, A, Y, then we go to QA. So we accept if any one of them accepts. And then also, if we get to reject, then we just skip right to the next one. We go W, P plus 1, P plus 1, and then epsilon Q0 W. And these 2 rules take precedent over those ones. Now, notice that I did say that we have to say that if all of them say no, then we stop. So how can we know that we've stopped? It's not obvious how to do that. Essentially, the way that we would need to do that is we would need to have another piece of the configuration. And what this piece of the configuration would be, it would basically say, I'm looking at paths of length k, and I have done an action that was not just going to a reject state. And if we ever see something that's not reject in the kth level of the tree, then we flip this bit. But if we get through everything of length k, and we've never flipped the bit, then that means that everything we explored of length k was all rejects at the bottom of the leaves, and then that means that there's actually no more progress to be made. So it's hard to write that down in this rule, but that's something that we need to do. Now notice that this configuration system right here maps very cleanly to using multiple tapes. We'd have one tape for W, one tape for the path, one tape for the rest of the path, one tape for the current configuration. And so this right here basically describes the setup of a multi-tape Turing machine that would work this way. And notice that it is time expensive. It's expensive in terms of time because we have to repeatedly go over earlier parts of the non-deterministic graph over and over and over again. So obviously what would be nice to do is talk about how we could do another version of this that was space expensive but time cheap. And we're going to call this the forking semantics. The idea behind the forking semantics is that we're going to say a configuration is going to be a queue of configurations. Okay? And configuration 0 is just going to be the queue that has epsilon q0w on it. All right? And here's the way that the rules is going to work. It's going to say that imagine that the top of the queue says that x, qi, ay, and then after that you have more configurations. Configuration 2 up to configuration n. Okay? Then if delta of qi a equals qj b, let's say that we're going right, then we're going to change that configuration to a new one where we have c2 ... cn, and then at the end we'll have our new configuration that says x, b, qj, y. And we're going to have a similar rule for going right, a similar rule for having a blank. Okay? And now we get the forking one. So what does the forking rule say? The forking rule says that if we go and we look at qi and a, and we get back two new states, qj and qk, and we were in a configuration where the first configuration at the top said x, qi, ay, c2 up to cn, then in that case, we're going to put c2, cn, and then we're going to have x, qj, ay, and x, qk, ay. So the idea here is that whenever we get a fork, we just create two configurations at the end. Essentially what this does is that rather than exploring this tree in a breadth-first way, where we repeatedly do the work to keep going down and coming back, what we're doing is we're keeping the breadth-first frontier as basically a queue of all the stuff that we've done. Now notice though that this makes it so that this queue of configurations gets larger and larger and larger as we keep going. So it uses a lot of space, but it doesn't ever redo work. This is essentially the two ways of implementing non-determinism in general. In general, the way that you do non-determinism is you either take a lot of time, where you repeatedly retry different things, or you take a lot of space, where you remember the different things that you were doing. And pretty much all AI and search problems have these two different ways of dealing with non-determinism. Because when we say non-determinism, we really mean deciding between two different choices. And that happens over and over and over again in so many different kinds of programming languages and models and problems and things like that. And basically they will use either one of these strategies. Now, how, of course, would we do the bi-simulation idea of this? I mean, basically, we sort of follow a same principle with the multi-tape Turing machines, where we encode these configurations by like putting a little hat on top of the A, using like the first character to indicate that it is like what the queue that we're saving is, and then we use like hashes between them, stuff like that. So it's fairly straightforward to do this. All right, so that's all for today. We are now, from this point forward, going to assume that we have non-determinism, and non-determinism has given us concatenation, so we've got union, intersection, concatenation. Obviously, we can get star, because star is just doing union and concatenation at the same time, right? Because 22.9, that A star is just equal to epsilon union A circ A star. So we can just use a union and a circ, and then we can get the same thing. So thus we can get the starring of languages inside of sigma 0 or sigma 1. Okay? But notice that we have not talked about how to do negation. So we'll talk about that next time. Okay, later.